Our final speaker of the session is Hadrian Paugnat from UCLA, talking about dark matter constraints from strongly lensed quasars.
Hello, everyone. My name is Hadrian Paugnat. I am a grad student at UCLA, working with my advisor, Tommaso Trejo, as well as collaborators Daniel Gilman and Anna Nierenberg. And I work on flux ratio anomaly statistics, which is a method to get constraints on the properties of dark matter using strong gravitational lenses. And today I want to present some recent advances in this field and discuss some perspectives for Roman. So we're looking at a particular type of gravitational lens, which is called the quadruply image quasar, and the name is fairly explicit. It is a background quasar that is lensed by a foreground lensing galaxy, such that from an observer viewpoint, we see 4 point sources in the observer plane. And the fluxes of those images are set by the intrinsic brightness of the quasar and the magnification along each of the line of sights. So if we take ratios of fluxes, the intrinsic brightness cancels out, and we're only left with the ratios of magnifications. So if we have an accurate model of the main deflector galaxies, in theory, we should be able to predict those flux ratios. What we see in practice is that sometimes an image is more magnified or more demagnified than what we expect. We call this a flux ratio anomaly. And we think that some of these flux ratio anomalies, at least, are caused by additional mass along the line of sight. So dark matter substructure, it can either be a subhalo within the main lensing galaxy's dark matter halo, or just a field halo along the line of sight. And this is interesting because, as other presentations have discussed, the subgalactic properties of dark matter depends on the particle nature of dark matter. So if we look at two popular examples of cold dark matter, a fiducial example and then a warm dark matter, these are simulations of Milky Way-like analogs. You can see just by eye that the structure on small scales is much more important in cold dark matter relative to warm dark matter. In warm dark matter, you have a suppression below a typical mass scale, which is called the half-molar mass. And so if we look at this from a lensing point of view, you can imagine that having substructure that looks like this will create more flux ratio anomalies because you have a higher chance of having a subhalo that is aligned with one of your line of sights. So there's two things to consider here. First, you need to not only consider individual subhalos, you need to consider entire populations of halos and subhalos. And then you also need to consider flux ratio anomaly statistics, because if you're just considering one system, then there's a chance that you're just well aligned if you're just lucky and you just have a good alignment between one of your subhalos and one of the line of sight. So you need to consider flux ratio anomaly statistic at a population level, and you need to do so on as large a sample as possible, and this is where Roman will really shine. Now there's a caveat, which is that we cannot simply use any flux ratios to do the flux ratio anomaly statistics, because the innermost regions around the quasar are microlensed, so their physical size, their physical size is small enough that they are comparable in terms of angular stars to the Einstein radius of individual stars within the lensing galaxy, which means that the flux ratios that receive contributions from the accretion disk, the innermost parts of the dusty torus, or the broadline regions can get microlensed. They can get perturbed by something that is not dark matter. So the microlensing signal is interesting in itself, but this is something that we want to get rid of if we're interested in measuring dark matter properties. So to circumvent this, we can use other emission regions like this warm dust region, which spans a few parsecs in size and dominates the spectral energy distribution in the mid-infrared around 10 microns in rest frame. And it's not microlensed, but it's very sensitive to perturbations from dark matter substructure. And we can also use this more extended narrow line region, which spans tens to hundreds of parsecs. And this is a very recent result that I wanted to present that introduces the first measurements of narrow line flux ratios for a length quasar using the James Webb Space Telescope, and specifically NIRSPEC IFU. So we have this beautiful IFU data for RxJ 1131, which is a quadruply image quasar. You can see the 4 point sources here, and there's also this very prominent lensed arc that we need to correct for, because this extended emission is not sensitive to perturbations from dark matter substructure. And if we look at the spectrum, there's a lot of features, including some broad lines that we do not want because they're microlensed. And we have this prominent S3 doublet, so we extract the spectrum from the quasar only in this spectral range, and then we perform joint modeling of the 4 quasar spectra to isolate the contribution only from the narrow line, and then we use those narrow lines to measure the flux ratios that then will go into the dark matter inference. So this is for the narrow line region. I also said that we can do similar things with the warm dust, and this is these are links to papers from a series of papers that presents results from a lens quasar survey using MIRI for about 30 lenses. And the idea here is that you take multi-band photometry for quadruple image quasars, you do a rough SED modeling, and you extract the contribution from the warm dust only to measure flux ratios, and then you use those flux ratios to do the dark matter inference. And so after completing this survey, we have about 30 quadruple image quasars that have precise measurement of flux ratios, and we can use those to get constraints on the warm dark matter. And this presents the constraints on the half-mode mass on the y-axis. So the half-mode mass is the typical mass scale below which there is a suppression of structure in warm dark matter relative to cold dark matter. And you can see that we're able to place an upper limit on this. So we're consistent with CDM down here, but then we're able to rule out some of the most extreme examples of warm dark matter. Now, this is where the field is right now. We have about 30 lenses that have solid flux ratios. What can Roman bring to this field? Well, one of the most limiting factors in this technique is the available number of quadruple image quasars. So lens quasars are already rare. Lenses are rare. Lens quasars are even rarer. And then quadruple image quasars are very, very rare. We only know about 100 of those systems. So I've said that the James Webb survey only has 30 of them. It's because some of these hundreds are not exploitable for the flux ratio anomaly statistics technique. So we'd like to know if we'd like to have larger sample sizes. And this is where Roman will really come in, especially the high latitude Y area survey. So I'm showing here numbers from a forecast that was done by Paris Sharma at Stony Brook. And I want you to focus on this column here, which shows the forecast for quadruple image quasars, or quads for short. And in total, the high latitude survey, medium and white tier, will image about 400 new quads. So it's a significant improvement in the number of available systems. And with 400 new quads, and even if we only use a fraction of those, we can get order of magnitude improvements on the dark matter constraints. So what I'm showing here on the right is a forecast that was done by Anna Nierenberg in one of those James Webb Lens Quasar Survey paper. And it shows, it's not exactly the half-mode mass, but it's a very comparable thing. Essentially, if you take a CDM-like subhalo mass function and brutally cut it off at some mass m low, then this shows the upper limit on this m low parameter that you can get as a function of the number of lenses. So we expect that there's going to be a similar behavior for the half-mode mass or any other lens model parameters. You can see that as you increase your sample size, you're able to place more and more stringent upper limits on these cutoffs in the subhalo mass function. And you also notice that we're less and less dependent on our choice of prior. So we're using priors for the amplitude of the subhalo mass function that are informed by semi-analytic models. And as you increase your sample size, you become less and less dependent on those priors. So it is really important that we increase the sample size, and this is where Roman shies, ranks the numbers, but we're also going to discover some quadruple image quasars with LSST and Euclid, and the other advantage of Roman is its precision. So it's going to have imaging data with Hubble-like quality for all of these 400 new quadruple image quasars. And that's important because once you have images that are sensitive with sharp and stable PSF, you can really exploit the information that comes not only from the quasar image positions, but also from these extended length arcs as the ones that I was showing earlier with NeurSpec IFU data. And there's two reasons why this is interesting. The first one is that if you can exploit imaging data from this entire lensed arc and not only from the quasar image positions, then you get more precise constraints on your lens model parameters, which in turn means you have better flux ratio anomalies, and you can improve the dark matter constraints. This is a simulation that was done by Daniel Gilman, essentially using 25 quadrupole image quasars. You simulate them using a ground truth, which is here consistent with CDM. And then you apply the technique that I mentioned earlier. And you can either use in gray only the quasar image positions and the flux ratios as your information to do the flux ratio anomaly statistics, and you get these gray posteriors. Or you can also add the imaging data from the lensed arcs, and you can see that it shrinks the posterior volume by quite a lot. So you're able to get additional information if you're using the lensed arcs. And the other thing that you can do once you have good quality imaging data is that you can better control your systematics that are associated with the lens modeling. This links to a paper that I wrote last year, where essentially it tests on simulated data the effectiveness of a local modeling approach as opposed to the more traditional modeling approach, which makes physical assumptions about the shape of the deflection field. This is a more agnostic way of doing lens modeling. I would love to go into more detail, but I think I'm nearing the end of my time, so I will leave it here. I will thank you for your attention, and we'll take any questions that you have. Thank you.
All right, thank you. Questions? Yes, there.
Just a quick question. Is there a preferred filter that you would, in terms of your measurements, or would you use, since lensing is achromatic, are you just going to use all of them?
Yeah, so it helps to have multi-band imaging data. It tends to, so there's advantages when you use redder filters, there are advantages when you use bluer filters. When you use bluer filters, you can have star-forming regions popping out in the imaging data, and those help because essentially gives you additional point sources to constrain your lens model. And then if you use redder filters, then it tends to have higher contrast between the lensed arc and the deflector galaxy. So there's advantages to having both, and having several filters to do the imaging data modeling really helps too.
Any other questions? Anna.
Maybe just to follow up along these lines. So once you say identify your new 400 lenses, like would you still want to get IFU spectroscopy to get even more information out of those?
Sorry, I didn't quite.
Oh, would you want to get follow-up spectroscopy for the Roman lenses?
Yes, absolutely. So this is something that I glossed over, but I spent some time saying that we need to measure the flux ratios in a way that is sort of smart. We need to isolate some of the emission regions in order to measure the flux ratios. So a lot of these systems are going to need some follow-up observations, either to measure the warm dust flux ratios or the narrow line flux ratios. Yes. There's a couple of them that will have some measurable flux ratios thanks to the GRISM data, but in general, the GRISM data is not going to be sensitive enough to do these high precision measurements, so we will use some follow-up observations.
When you study these, do you separate them into samples of elliptical galaxy lenses versus disk galaxy lenses?
Yeah, so exactly. This is why we cannot use all of the known quadrupole image quasars. We want to only focus on those elliptical lenses because disks can create flux ratio anomalies that are not substructures.
Hi, really nice talk. Maybe you mentioned this briefly. So you have the constraints using MIRI right now, and you said that more samples will give you more statistical power. But what about the systematics of Roman, like PSF size and pixel size come to the picture how much will that affect on those constraints?
So we currently have some similar systematics that we have to deal with whatever data that we're using. So there's systematics that are associated with the Mary data, and we try to model those to do these constraints. For the Roman data, it's going to be the same. The Roman data is not going to be used to measure the flux ratios, but rather to have good quality imaging data. So in that sense, it would be similar to having HST imaging for all of these lenses, which, as I've shown, really helps with the strengthening of those constraints.
Okay, thank you.
All right, that's all the time we have. So let's thank Hadrian and all the speakers from this morning, please.